Welcome to this video on X-ray production and diffraction. In this video we're going to see more confirmation of the interaction of photons, electromagnetic rays, and their interaction with matter, as well as another instance of diffraction and interference, which supports the experiments that we've been looking at so far. So we're going to look here at a very crude representation of a vacuum tube. So the vacuum tube is this glass space over here where we have a vacuum on the inside, which means that all the particles that would make up sort of the gas fill in here would be removed so that electrons could move without any hindrance or interaction with things in the chamber. So over here what we actually have is a some sort of accelerating voltage source, but in this form it's going to be attached to some filament, so you can kind of think of a little light bulb here, or a very strong light bulb for that matter. And we're going to do something on the order of about, let's say, 70,000 volts. And through a process called thermionic or thermionic emission, this is where electrons are emitted through some sort of heat process. You don't have to know very much about that for this particular video. That's just the mechanism by which these are released. These little electrons, which here are not so little, they kind of look like monster electrons, they have extremely high kinetic energies. So they're moving very, very fast across this space. And they're targeting a copper block in this experiment. Now this copper block is going to try to stop these electrons. And so Wilhelm Röntgen was building vacuum tubes, and he was trying to see what happens when you get electrons really, really high speeds and you slam them into metals. You know, what it could happen, what might happen. And what he was picking up was that once the copper was hit with all these very high speed electrons, some sort of radiation was being released. Now we're saying radiation in the form of photons or waves. So he was detecting this very high energy radiation coming off of the vacuum tube, and it was you could calculate it using the energy equation again. And we see that the frequency, which is fairly easily detectable, represented or was directly proportional to how much energy these waves had. Now they're extremely high energy, and that extremely high energy was strange to Röntgen. He wasn't sure exactly what was causing this. He was just picking up this residual radiation. And he termed these photons, or these rays over here, X-rays, because, as we always say, when we have something unknown, we refer to it as X. And he said, well, I'm going to call these X-rays because I don't know what they are. And the name stuck, and now it's part of the electromagnetic spectrum right over here. Now it turns out that this is one of the highest energy forms of EM radiation. So over here on this end, we know that we have relatively long wavelengths, sometimes extremely long. These have very low frequency waves, and thus they have very low energies. Where on this side, we're going to have very, very short wavelengths, much higher frequencies, and much higher energy. Now when we're talking about different forms of radiation, we can think that X-rays can move straight through your hand, let's say. They can move straight through paper. They can move straight through wood. They're really only stopped by things like lead and other materials that are pretty thick. So when you put on a lead vest when you're getting an X-ray, it's to help protect the rest of your body from the residual very high energy X-rays that can storm your body. And so when we look at this perspective here, we see again that the photons, which are these little energy packets that make up electromagnetic waves and light, these are behaving in interesting ways. We're seeing them behave as waves and interacting with matter. So they're exhibiting once again this wave-particle duality. And the wave-particle duality is this almost double nature of these kinds of materials. Now if we think about it, the energy that the electrons had while they were moving across, E1, I'm going to call that, we could calculate that roughly by saying the charge of the electron times the potential difference with which they are accelerated and released. They then hit the copper block, and we're going to say that their energy reduces dramatically down to a value of E2. So the change in the energy of the electrons could be written as E2 minus E1. And the difference in the energy of the electrons before and after, because we can have some sort of electrical detection here to see what speed or what energy these electrons have. The difference between the two states of energy is the energy of the X-ray. And the emitted X-rays can be calculated with H times F, as most of our other photon energies have been calculated. And so we can see that there's some sort of conservation of energy happening here, and a very interesting emission of photons when particles have some sort of interaction. So again, we're seeing this wave-particle duality of nature. The phenomena is that particles and waves arise from one another or can act like one another depending on the situation. Now, the mechanism by which this occurs, we have not talked about yet. So why is it that photons are released in these experiments? Where are they actually coming from? What's happening on the subatomic or the atomic level? Well, this is what we're going to start to explore in the next section as we take a look at the Bohr model of the atom and how electrons occupy the space surrounding the nucleus. Before we get to that in the next video, we just want to take a very quick look at the very cool electron diffraction that can occur. And you can see here in these images that an X-ray tube, that was the tube that we were just talking about, where we will accelerate electrons, smash them into metals, and they release X-rays. They can actually be sent through a crystal again, like we were seeing before, and they will form these really awesome patterns on film. And so these electron rays, we are seeing a very similar thing in the form of diffraction as we did with light and other kinds of waves. And this is just supporting the idea that this is light, that or X-rays are electromagnetic waves, which is also light. Here's an image, a film slate of the X-ray diffraction, excuse me, and you can see the very cool pattern that is made. Again, it's all forming from the X-rays hitting off of different levels of the crystal, and the path difference, d sine theta, again, being crucial to determining whether we will have constructive or destructive interference when these two rays recombine again on the other side. So again, we're seeing support for all of the other hypotheses and other experiments that were done. In the next video, we're going to take a look at the atomic structure and start to see how is it possible that this kind of energy is released.